Welcome to Data Skeptic. Data Skeptic brings you discussions about how data is changing our world. Our interviews are conversations with thought leaders in topics like data science, machine learning, and artificial intelligence.
So I'm here at NIPS with Risto Miikkulainen. Thanks for joining me.
Thank you.
You're a professor at University of Texas Austin and the VP of Research at Sentient.ai.
Yeah.
So there's a lot of industry and research going on at the moment in areas like this. Let's start with your research. Tell me a bit about the areas you have been interested in.
Yes, I've been interested in neural networks my whole career since the 80s and applied them to a couple of different areas, cognitive science, computational neuroscience, understanding the brain, understanding the cognition, but most recently using them to build agents, intelligent agents for games, for robotics. And that takes a little bit different technology, using evolutionary computation to design your neural networks for you, which is different from the usual neural network technology, which is deep learning, backpropagation, even supervised learning, and reinforcement learning are a little different. That's my niche, using evolution to build these intelligent agents, and that's what my students are doing and what we're also doing at Sentient.
Tell me a little bit more about the distinction there between a neural network trained with backpropagation, which I would imagine if you know what deep learning is, you probably know backpropagation. What's the advantages I can get out of evolutionary computation?
Yeah, so they apply to very different problem settings. So for backpropagation, you need labeled examples. You need to know what the correct output is for a given input. It's become big because now we have big data sets of that kind. And there's a lot of good things that we can do with it. Evolution has a different setup. We don't have labels. We don't have targets, supervised examples. We don't know what the correct actions are. Instead, you have an individual and you test it over a period of time and you see how well it's doing, without ever knowing what the optimal actions might be. And that is feedback for the algorithm that then allows you to discover more agents of that sort, explore the whole space of agents, and find where the best agents are. So in that sense, it's similar to the reinforcement learning setup. You are getting reinforcement type of information, but the reinforcement can be very sparse. So you may, for instance, play a lot of video games or have a robot that performs a lot of actions, and you eventually get an evaluation of how well you're doing. You use that on a population of agents. So that's the difference between reinforcement learning and evolution. In reinforcement learning, you have an individual agents that you are constantly improving based on reinforcement. In evolutionary computation, you have a whole population, hundreds of agents perhaps, and they are supposed to be different. So they're supposed to explore different parts of the solution space. And continuously, in parallel, you're running multiple searches. So you're not refining one agent, you're refining a lot of different agents. And that's where the difference is, and that's where the power comes from evolutionary computation, that you can be more diverse and can find novel solutions, things that are hard to find, difficult to find. And that, I think, is the excitement. It applies to problems that are difficult to define, difficult to evaluate, difficult to make progress on.
So when I think of evolutionary algorithms, I think, as you described, there's a pool of whatever solutions, in this case agents, and I'll see how they perform, I'll mutate some, I'll cross-cut some, I'll kind of come up with the next generation. What are the free parameters that you work on in your research?
There's a lot of excitement recently in the evolutionary computation community about an approach for novelty search or behavioral diversity. There are several different names for that. But the idea that we shouldn't just reward the agents that are good in the performance metric, the fitness metrics, or the reinforcement that we have, we should reward those that are different, that are novel in some way. And since we have a population, we can do that. We can have a secondary metric, or maybe the sole metric, to be different from others. And this makes sense from the evolution point of view, the biological evolution, that evolution in biology, in the world, discovers all these different niches. Animals that survive by being different from others and finding some way of surviving that others haven't discovered. And we can utilize that. This is the new direction in the last few years, and it's turned out to be very powerful. It allows you to discover solutions that are hardest to discover. So for instance, if you have something that's like a cognitive function, memory or learning, that is something that needs several steps in development before it can be discovered. And those are detrimental. They don't help you in the meantime. So we need to encourage diverse behaviors, diverse actions, diverse structures. And then eventually, they serve as stepping stones. And we can combine then two stepping stones that either one wouldn't really do much, but when you put them together, you get something that's novel and complex. And encouraging that to happen, encouraging diversity, novelty, encouraging stepping stones, and then methods that utilize those stepping stones. That's where the research focus has been recently. Not just mine, but the community as a whole. But I think that's the most promising one. And that's also something that's difficult to do, say, with reinforcement learning, where you are indeed incrementally, step by step, improving what you have. But here we are doing just the opposite. We are spreading out as much as we can, finding novel things without really even knowing necessarily what we are trying to discover. And then we are trying to utilize those stepping stones to find something that's so complex that you could not find it by incrementally changing things.
When we do traditional deep learning, it's going to be sort of one large network that we're training with a vast amount of computational power. There's been a lot of good papers at NIPS this week about how we might be able to distribute that, but in some sense it's sort of a single network kind of framework. Is one of the advantages of a more agent-based approach that it's sort of embarrassingly parallel?
That's definitely the very nature of evolutionary computation, is that it's embarrassingly parallelizable. So you can put the entire population, evaluate every individual in a separate machine, and you can really utilize the computing power that way. And that's why evolutionary computation has surged forward so much in the last few years. It's also an approach that can utilize that power. I mean, downstairs in the exhibit hall, there are these new architectures, Intel, NVIDIA, IBM. Everybody's coming up with big ideas about how to take computing forward, hardware forward. And much of it is parallelism, and much of it is AI-based or AI-focused. So what can take advantage of that? Well, definitely evolution. We can utilize all that computing. Let's just take an example. We have a symposium this afternoon on meta-learning, which is the idea that you have a learning mechanism that optimizes a learning algorithm for the lower level, for the neural network, for instance. So it could take a form of evolving the network structure, network hyperparameters, network components of a deep learning network, for instance. So now a deep learning network takes 2 days, maybe a week to train if you have a big one. Now you have a population of 100 of those, and you want to evolve them over 100 generations. That's a lot of computing power. And it's put to good use. You can discover structures that train much better than anything that humans can design. And it's based on utilizing the computing power in a principled way. So that is a big direction and a big opportunity for evolutionary computation.
You'd mentioned creating video game agents. When I think of agent design, I want an agent that's going to maximize some function. You know, it's going to win the game, escape the maze the most quickly, whatever. It seems to me that a well-designed video game agent would make the game not fun.
Yes, that's a very good point. Indeed, in evolutionary approach, you can decide what your goal is, what your fitness is. And it could be maximal performance, play the game as well as possible. And if you do that, you indeed get an agent that does not play like a human and plays too well. There was a competition called Bot Prize that ran for 5 years, 2007 to 2012, where the goal was exactly that. How can we design a game agent that plays like humans? And it turns out that makes it more fun for humans to play against other agents that are human-like, even if they're bots. And when we started, we did not know whether that was possible or whether it was even a question that was worth asking. But it turned out beautifully, and we learned a lot from it. We learned exactly that. If you optimize for performance, you get something that's not good, not fun, too good. Agents that run very fast, jump, and shoot accurately at the same time. Agents that react very fast, no matter what happens. People don't do that. So what we had to do instead was to pose some restrictions. You cannot do multiple things well at the same time. You wouldn't even try. You are startled sometimes. And limitations on memory, limitations on reaction times, and so on. And then when you optimize under those constraints, you get behavior that looks like people. Indeed, Bot Prize was about being indistinguishable from humans. And in 2012, 2 of the teams in that competition won that prize. They were judged, their bots were judged human 50% of the time. And that was better than half the humans. so that we can say that at least in that kind of evaluation, we can do pretty well in directing the behavior to the kind of behavior that we want. It's not necessarily the best behavior, but it's behavior that's interesting or human-like or worthwhile. And there's that flexibility in the approach.
When recruiters are asked what is the number one skill they look for in business school graduates, the top answer is analytics. Analytics used to be a luxury in the business world. Today, it's the default. With a Master's of Science in Business Analytics, or MSBA, you could get qualified to apply data insights to real business situations. The Mendoza College of Business is a comprehensive business school at the University of Notre Dame. Their MSBA program is ideal for the business decision maker who wants to master the craft of analytics. Find out if this MSBA program is a good fit for your busy life by visiting mendoza.nd.edu/dataskeptic. Use the code SKEPTIC to get your application fee waived so there's no cost to apply or explore this opportunity. Once again, visit mendoza.nd.edu/dataskeptic.
what are some of the exciting things you've seen come out in the field recently? I know there's a lot being published in evolutionary algorithms. Are there any major breakthroughs that strike you as being really noteworthy in the literature?
Well, yeah, the novelty search, I think, to me is the interesting recent development, and also some of the results that scale up, the kind of problems we can solve. So recently, Kain-Moydeb, for instance, showed that you can solve a 1 billion variable problem. And, typically we talk about dimensionality of 10, 20 being high. Turns out with these techniques, you can solve a problem that has 1 billion variables. I think that's really exciting, because that suggests that we barely scratch the surface. We can really scale up this approach and address problems that are complex about world economies, for instance, optimizing policies that happen in the real world, traffic allocation, all kinds of things that we haven't even been able to touch before if we use this technique. So I think that's really exciting.
That's a more recent technique. A lot of the techniques we started talking about, neural networks, they've been around for quite some time. It's just that engineering has caught up. We now have the hardware where we can solve these things at mass scale. Leads us to a lot of interesting industry applications. Maybe it would be a good time to transition into talking about what you do at Sentient AI.
Sentient is an AI startup, has been around for 10 years, but it started before the AI excitement started.
Right.
And it also started with evolutionary computation, which was and still is kind of outside the mainstream. For instance, in NIPS, there is not that much evolutionary computation. It's its own community. Gecko and IEEE have evolutionary computation conferences. That's a unique focus for Sentient, use evolutionary computation to optimize various domains. So stock trading is the first one, which is a great first application because you don't have customers and you don't have to deal with all the complexities of that. And if you're successful, you can fund yourself very quickly. But then we expanded to other areas of AI, in particular to e-commerce, optimizing web interfaces. You go to a website, and if you have a right kind of design, you're more likely to convert. Click the button that says buy or sign up or an action like that. And it turns out that's a whole industry, conversion science. And people are doing A/B testing. They're testing 2 alternatives to see which one is better. And that's pretty much, using statistics to do that, is pretty much where the state of the art was. And we brought evolutionary computation to that, showing that you can actually evolve those web interfaces. And evolution discovers solutions that human developers miss. So for instance, optimizing a call to action widget, evolution came up with bright colors, garish designs. The human designers thought that they called it the ugly widget generator, but it actually converted 45% better. It was the kind of thing that evolution finds. It does not have the same preconceived notions that humans might have, and it can discover solutions that are more effective. And that's one example of it. So there, the design is done by AI, by the evolutionary algorithm. And now we are applying that to other domains as well. Turns out there's a lot of problems in the world that have that nature, that we have data and we can use, say, deep learning to predict what will happen. Financial markets, one example. Whether a user will convert is another example, but there are many others like that. Health prediction, where somebody's health is going to go. Even blood pressure in an emergency ward, you can predict whether somebody's going to go to a septic shock, for instance. Those are some of the things we've done. Now, the question then is, what do you do about it? And that's where the evolutionary computation comes in. We can bring in evolution to design an intervention, some action that changes the future, not just predict it, but change it so that it will go where you want. So you could, for instance, optimize an intervention in the emergency line, the minimal intervention that prevents you from developing a shock. Or health intervention. You can look at the time series and see that this is not going well. What's the minimum suggestion we can make? Or one exciting application we are working with MIT Media Lab, Caleb Harper's Open Ag lab there, is cyber agriculture. So you have contained environments, they built them, where everything that goes in, water, temperature, light, nutrients, is computer controlled. And now when you can do that, turns out we don't know what to do with it. How do you actually, what is an optimal recipe for growing basil, for instance? We don't know. And that's where we bring the AI in. We use neural networks, perhaps, or some method to predict what the effect would be if you give them the certain recipe. And then we use evolution to optimize that recipe. And again, we discover things that we didn't know. For instance, in this case of growing basil, we thought that basil needs to sleep at least 6 hours. We give it darkness 6 hours. But evolution very quickly, in a couple of iterations, discovered that that's not true. Basil thrives if it sees 24 hours of sunlight. And indeed, that was a recipe that was a surprise for biologists in the team, and we got best results from that in just a few iterations. So it's again an example of taking a domain where humans have some intuition, perhaps, and they've been doing the same thing for a long time. But if you can formalize it as an optimization problem, then evolution can discover novel solutions and do better.
Going back to your A/B test example, I think everyone who listens is going to be familiar with the very basic idea of, should it say marketing message A or B, and you do chi-squared test or t-test, some simple statistical thing to evaluate which was better. And there's some pitfalls there about effect size and whatnot, but for the most part, it's pretty straightforward. When you describe that evolutionary algorithms could find really novel things on the page, I'm trying to conceptualize that from an implementation point of view. I guess HTML pages are strings. In that sense, they're like DNA. You can cross-cut and mutate them and whatnot, but that seems like there's too many degrees of freedom there. How do you practically do something that runs in a reasonable amount of time?
Yeah, that's exactly where the power is. The search space can be huge, even with just a few elements and few values for each. You have millions of potential web pages. But evolution is sometimes incredibly effective in finding good solutions in just a few trials. And it doesn't mean that it finds the very best one, if there even is one. But there's no guarantee, and you never know. But you, of course, know that you make progress and you find out better solutions. So there are examples, for instance, in multiplexer design, which is kind of a benchmark to evaluate algorithms. The space is humongous, 10 to the 616, for instance. And we've solved even bigger ones, 2 to 2 to the 71 or something. It's inconceivable how large it is. And through evolutionary optimization, we can find the correct solutions, correct multiplexers in some 100,000 trials, which is doable. So if the space is like that there's structure, that you can find interactions and building blocks, and then put those building blocks together, evolution can be very effective in a humongous search space. And that seems to be true of this domain as well, designing web pages, that there are interactions between colors, between texts, background images, and they may not be obvious to human designer, but evolution can quickly discover those and then start using those building blocks and very soon have a page that is a good design.
But do you have to provide the algorithm with some set of actions it can take? Is it just like it's controlling CSS features, or how do you actually go about implementing?
The simplest approach is that there's a human designer that comes up with the search space. So these are the elements.
I see.
These are the values I'm allowing the evolution to discover or to modify. And then it can still be millions, but it comes from humans. That's a starting point. So when you take something to the real world, you have to talk the language of the people who are going to be using it. So we have to start with something that they're familiar and comfortable with. So that is it. They have still control over the design of what the elements are and how you can manipulate. What is the search space? And even in that search space, there are solutions that are overlooked. In the future, we can open that up. We can have a much larger search space. The evolution algorithm can discover its own components, own elements, design different values. We can have, say, colors be continuous colors. There's a lot more expansion that can be done, but the starting point is already beneficial.
When you describe the Basel example, it's very interesting because it sounds like a very controlled lab situation. So in the same way, the solution space can be defined by biologists or whomever, and then evolution can solve it. And kind of you can control everything, temperature, humidity, whatever you want about that environment. The web page has all these presumable latent external faculties. What day is payday could affect how many conversions you see, things like that. How much noise does that add, or can you even model some of these externalities?
Yes, so what I didn't say yet is that application of web page design is interesting in that we do that in real time with real users. So whenever evolution algorithm suggests a page, that's actually shown to users, and we see how well it converts. This is how A/B testing is done as well. There are indeed lots of variables that we don't see. That's the next step. That's what we're working on now. We call that order segmentation. So we not only show the pages, but we look at who's coming to the site, what time of the day it is, what day of the week it is, what kind of service provider is the user using, is it desktop, is it mobile? There are lots of variables that we can get immediately. And in many sites, there's even more. If they log in, we know a lot about them, like what they usually buy, and so on. All that information can be input to the system. But now we no longer evolve one single web page that would work well for everybody. But we put a neural network in between. The neural network gets those variables that describe the user, and as its output, it gives you the design. What values for each element. And now we evolve that neural network. We evolve a mapping. And that's a continuous mapping. Whenever a new user comes in, we query the neural network, we get a page. And this way, different groups of people will get different pages. And in some preliminary experiments, this really works. We discover several different groups, and we also have continuous interpolation between them. And a lot of that noise is taken into account. It actually becomes a variable in the system. It's something that we utilize instead of have to tolerate.
So I was reading a little bit about the AI platform that Sentient.ai has built. Can you tell me a bit about it?
Yeah, so this is the technology that we have built first for these applications. Like a lot of the evolutionary computation methodology was developed for stock trading, and then the deep learning methodology was developed for visual interface to catalogs. And when you build them for a couple of applications like that, you find that there is a core that repeats over and over again. Like, for instance, this idea that you have a model that allows you to predict, and then you have an optimization system that queries the model, optimizes it, and then occasionally you send something to the the containers to grow Basel with.
Mm-hmm.
That technology is brought together to the AI platform. And now the idea is that once we have it, we have extracted it from several applications. And it's also something that then can apply to numerous new applications. It's not everything under the sun, but it is indeed this modeling and optimization platform that Sentient builds.
Very neat. Is it something that people can subscribe to, or is it an internal tool?
It's internal at the moment. We're building those new applications and considering what to do with it, what applications are the best. Now there's an open source component called Studio.ml, which is a tool for running experiments. So one of the true pain points, so anybody who is doing data science experiments, is just managing the experiments. What did you do here? What parameters you change? Did you do hyperparameter search? All of that is very hard to keep track of and run automatically. So Studio.ml was built first for us because we needed it, but it also turned out that everybody else needs it too. So we decided to open source it. So that's something that anybody can download and run, and it helps you manage your experiments and help you with the experiments like doing hyperparameter search.
Yeah, well, and you get data governance out of it now too. You have full or provenance, you have traceability of everything that was run.
Exactly, yes.
Where can people go to learn more about that?
Well, there's a website. Sentient website always has pointers to what we do and what we make available, and blogs that describe, for instance, the CyberAct project and other projects. So Sentient.ai.
Cool. I'll have a link to that in the show notes so people can check it out.
What I'm most excited about is that we have a new influx of people into this area and with different backgrounds. And I think that this is, being an evolutionary computation researcher, I know that diversity is everything. so I love the idea that there's...
Sorry, it took me a second. That's very good.
Different people coming in with different ideas and then having a forum like NIPS and other conferences to explore those ideas and exchange those ideas, I think is wonderful. So stay engaged.
Absolutely. With that in mind, are there any areas you think are untapped opportunities in evolutionary computation, places people haven't taken it yet?
Well, they tend to be the ones that I'm mostly concerned about. And I think that one big thing that we haven't yet done is experiment with huge amount of compute. We see that coming out, and it is a hunch that if we actually can harness that, we can tackle a question like evolving a neural network in a large scale. We see these very complex architectures that people are proposing for neural networks. And I would really like to be able to run an experiment for an extended period of time, having thousands of GPUs at my disposal, and then techniques that allow that to happen. It is something that is very compelling. It hasn't happened yet. It's also something that is not really easy to do because you have to gain access to it. But looking around, Intel, NVIDIA, IBM, others developing, Google are developing these systems that make it possible. So more power to them.
Yeah. So nature, in some respect, has conducted a very long-term experiment that's produced this machine we call the human brain. What sort of long-term experiment are you thinking about?
Well, online evolution, something that you don't turn off, that keeps running. And many of these applications actually have that nature. Even the web page design. You design a page and it works for a while, but then seasons change, fashion changes.
Yeah.
There are world events. So I think that this is an important direction. Continuous optimization, always on optimization, and applications that come with it. It's just barely starting because we just barely have applications at all in the world. But this is a new direction we have to deal with. And I think it's solvable. It's not a huge challenge. How you do it so that you don't harm your performance and make mistakes along the way that are costly, that's where the research has to go in.
Excellent. Well, Risto, thanks again for joining me. This was a great conversation.
Yeah, been fun. Thank you.
Data Skeptic is a listener-supported program. To support the show, visit dataskeptic.com and click on the membership tab.